Awesome. Okay, cool.
Greetings again from the 403 to the HAZ, Mr. Nelson. Very happy to see you. We are learning about logarithms. This is pre-Cal 12, and in the last couple videos, we were just introducing logarithms. We were just learning how to convert between the inverse form and then the logarithmic form, because a logarithm is essentially the inverse of an exponential function. But we work with logarithmic form because some mathematician much smarter than me once upon a time said, hey, when I put the letters L-O-G together, it makes magic. That's not how it happened, but that's what I'm going to say. But guess what? The theme of pre-Cal 12 is function transformations, and just like we were able to transform baseline functions and radical functions and exponential functions, yes, man, these are dirty. Holy crap. I just want you guys to think I'm smart. Just like every other function we deal with, we can transform a logarithmic function. But in order to transform a logarithmic function, we need to actually have the baseline function. And just like in quadratics, our baseline is y is equal to x squared, or in radicals, it's y is equal to x. This is what we transform, this is where we start. We have c to the x for exponentials. Logarithms, our baseline function is y is equal to log base c, my constant, x. Okay? This represents the inverse of this. Okay, so this is our starting point. This is what we're going to transform. And guess what? It looks exactly the same. So let's put this baseline function, our starting point, y is equal to log of some constant base. And remember, if I don't write a constant here, I just write kind of log of x, I assume it's base 10 because we approach our world from a base 10 perspective. That's just what we've gone with. So this, if there's nothing there, you can assume it's 10, but for all intents and purposes, we will write constant. Okay, this is our starting point. Now our transformed function can look anything like this. So it's going to be y is equal to a log, open bracket, b x minus h plus k. All right? It kind of looks similar to all the other transformations. I have never taught this before. I haven't even had a chance to teach this to my students, to you guys, my Hazelton Spartans. So I have to check my notes because I am teaching this right now for the first time since I took it myself. But we'll do it. Okay, so here it is. And guess what? Nothing has changed from any of my other function transformations. A and k are still going to be vertical transformations. They are going to manipulate my y coordinates, okay? And again, h and k, they are going to be my horizontal transformations. Okay? They are going to mess with my x coordinates. And A still behaves the exact same way as it ever has for any other function transformation. A represents my vertical stretch or compression. I might stretch it vertically or I might squeeze it vertically. Okay? And we've by a factor of the absolute value of A. Okay? So if I have a negative 2 here, it's going to be a stretch by a factor of 2. I'm going to multiply all my y coordinates by 2. If A is negative, it's going to be a reflection. I'm just going to make sure. Okay, yeah, it is a reflection in the x-axis. So I wanted to make sure it wasn't reflected in y is equal to x. Reflection in the x-axis, if it's negative, and if A is any number bigger than 1, it's going to be a stretch. If A is equal to 1, nothing happens. And so if A is between, the absolute value of A is between 0 and 1, we're going to get compression, just like every other function transformation. And if A is bigger than, the absolute value of A is bigger than 1, it's going to be a stretch. Okay? And I'll do K here. K is easy. K is just my vertical shift or translation. Vertical translation, which is just another word for shift. Okay? So if K is positive, I'm just shifting my logarithmic function up. If it's negative, I'm just moving it down. Easy. And I always do my A and my B. I don't know why I wrote this wrong. I'm sorry, guys. This should have been B and H. I apologize. I always apply my stretches, my A and my B's, before I do my shifts. So I would multiply my y coordinates by A, and then add K, and we'll see what that plays out as. But now we're going to do my horizontals, my B and my H. And my horizontals, my B and my H's, they're a little quirky compared to A and K. They're just they just behave a little differently, and by now, hopefully, we understand that. So with B, that's my horizontal stretch. But it's by a factor of 1 over the absolute value of B. So if I have a B of 2 here, I'm actually going to be shrinking it by a half. I'm going to multiply all my x coordinates by a half, by 1 divided by 2. If this was 1/2 here, well, 1 divided by 1/2 is 2, so then I would actually be stretching it. So if B is negative, it's going to be a reflection in the y-axis. And so then if B, the absolute value of B is between 0 and 1, so if it's a fraction, well, 1 divided by a fraction will be a stretch. It'll be a number bigger than 1, so it's going to be a stretch. I'm going to multiply my x coordinates by that. And if the absolute value of B is greater than 1, 1 divided by any number bigger than 1 is going to be a fraction, so I'll get a compression. I'm going to be dividing my x coordinates. Okay, so it just kind of behaves opposite to A. And H, also a little quirky, is my horizontal translation or shift. And if it's negative h, it means we're moving to the positive, and if it's a x plus h, it means we're moving negative. It just behaves the opposite, just like B. It's a little quirky. Okay? Nothing has changed. A, B, H, and K all behave the same way. So let's see what this looks like now in practice. We'll do a couple examples, and it's going to be the same thing. We're going to create a table of values for our original function, this guy, and then we're going to just do we're going to apply the transformations. Very, very straightforward. Let's do it. Okay. So I'm going to leave this here. I think we can get away with it leaving it there. So let's say I have a function, okay? And this first one we'll just deal with h and k. So let's say I have a function, and it says, okay, I want you to transform, to basically graph this transformation. And they say the transformation is as such. Log base 3 x plus 9. Yeah, thank you, Bill. He's telling me my keys were in the door. I find it. I left them there on purpose. Okay, we need to do this transformation. So the first step is, okay, well, what's our baseline? Where did this come from? Well, we know that it looks like this, okay? And so I already know that, okay, well, c is my 3. So my baseline function on this bad boy was y is equal to log base 3 x. That 9 and that 2 were added on. There's nothing in front of my log and nothing in front of my x. So I don't have any a or b's here. Just an h and a k. Okay, so let's create a table of values and see what that looks like. Okay, and it's not the easiest thing to do because basically when I'm creating my table of values for my original function here, I'm probably going to have to use the inverse form because this is basically just representing, if my original function was c to the x, this is representing my inverse, which is x is equal to c to the y. So x is actually going to be a function of y. So what I'm going to do is create my table of values. I've got x, and I've got y, and I'm going to use x is equal to c to the y. And if you don't understand what I'm doing here, you probably need to go look at my understanding logarithm videos. But these two are the same. I'm just using my exponential form here. So I'm going to use y's of, what did they use in the textbook here? I'm going to use y's of 0, 1, 2, and 3. Okay? So my constant is, so this is actually x is equal to 3 to the y because my constant is 3. So what's 3 to the power of 0? Anything to the power of 0 is 1. What's 3 to the 1? 3. What is 3 squared? 9. What is 3 cubed? 27. Okay, there's my original function, which I can draw a graph for, and it would look something like at x is equal to 1, I'm at 0. At x is equal to 3, I'm at 1. At x is equal to 9, I'm at 2. Right? So it's gonna, if I were to have used, anyways, this is what the function would look like, something like this. Okay? I'm not lying to you guys, but I have ever lied to you. And what we know is that we are actually never going to cross into negative x because it doesn't matter what y is, even if the y was 3 to the power of negative 100, that would just be equal to 1 over 3 to the 100. It would just become, basically it approaches x is equal to 0 without ever touching it. That's how logarithms work. So we have our original function. Now we can start doing our manipulations. We're going to create our transformed table of values. Okay? For x prime, y prime. Those are just my I'm just going to call those my transforms. So I always start with my a. I apply my stretches to my x or to my y and x coordinates. But I don't have anything in front of my for a or for b. So a and b are 1. They're not 0, they're 1 because 1 represents nothing changing. However, h, I have a plus 9. So I know when h is positive, it means I'm subtracting. So I'm going to find my x coordinate. 1 minus 9 is minus 8. 3 minus 9 is minus 6. 9 minus 9 is 0. 27 minus 9 is 18. Those are my transformed x coordinates, and the corresponding y's, I'm just going to do, remember, a and k vertical. So k, I'm just going to add 2 to each y coordinate. So 0 plus 2 is 2. 1 plus 2 is 3. 5. And wait. 4 and 5. Okay, and so if I were to regraph this, basically I'm moving my graph left by 9 units and then up. So it would probably look something like that. Okay, this is my transform function. And it's the same approach I've taken for every function transformation. I take a table of values and I manipulate it. Let's do another example. Probably a fine, well, shoot. Yeah, I think this is a good one. This will be just fine. This will be just fine. It's gonna be fine. Okay? So let's say I want to be able to graph or do a table of values for y is equal to negative log of 2x plus 6, and I'm going to say plus 2. Okay. Oh, and what was my base there? It's a base 2. If I didn't put that 2 there, you'd have to have assumed it was a 10, but I put a 2 there. So, step 1 is let's figure out what our original function that this transformation is based on, and that's easy enough to do. Looking here, it's just going to be equal to log whatever my base is, which is 2, x. There's my original function. Okay, so now let's make a table of values for this function. And in order to do a table of values without having to use a calculator, I'm going to convert this into its exponential form, which is x is equal to 2, which is my base, or c, 2 to the y. So x is actually a function of y in this case. That's what this represents. So I'm going to use 0, I'm going to use the same value, 0, 1, 2, 3. Okay? 2 to the power of 0 gives me x. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of y is 8. There's my original function. And again, if I were to chart this, it would look logarithmic. It would look something like this. Okay, I am not a graphing calculator, but I'm working on it. Okay, now we have everything here. We have something for a. It's a -1 now, which tells us it's going to be a reflection. It's not going to be any stretching because it's still 1. It's a -1. If there's no number, you just assume it's -1. A is 1, so it's not a stretch or a compression, but it is a reflection along the x-axis. I have also a vertical transfer shift of +2. Now, it looks like my h is +6, but that's not actually correct because I have to be in this form to figure out what b is. Right now, and so that means I have to factor something out here, which clearly 2x and 6 have a 2 in common. So I'm going to rewrite that. Right now, I'm going to rewrite this. Okay, what I'm going to do is I'm going to erase this, and I'm going to put that here. Y is equal to log base 2 of x. And then I'm going to rewrite this in a more useful fashion. So I'm actually going to color coordinate them. -1. This is base 2. Now I can factor out that 2, which is going to become my b. X. If I factor out a 2, it's going to be a +3. And then I'm going to have a Okay, so now I'm color coordinated. Red is vertical, blue is horizontal. Okay, now that is precisely in this form. This is great. So what do I have here? Let's collect, let's see what I've got. So A is -1. So I'm going to multiply all my y's by -1, and then I'm going to add +2. Okay, so let's do that. Let's do that. So, A and K, they deal with y coordinates. Y coordinates are right here. So I'm going to multiply them all by -1 and then add 2. 0 times -1 is 0, plus 2 is 2. 1 times -1 is -1, plus 2 is 1. 2 times -1 is -2, plus 2 is 0. Can you see a pattern here? I bet you the next one's going to be -1. 3 times -1 is -3, plus 2, -1. Here are my transformed y coordinates. Now let's figure out what the corresponding x coordinates will be by using these here. And to do that, eye contact. To do that, I have to pull out. So B I know is at 2, but that means that I'm going to actually do a 1/2. Remember, that's how B behaves. I've got to do 1, so I'm going to multiply all my x's by 1/2, not by 2, by 1/B. And then I'm going to, it's +3, then I'm going to subtract 3 then. It's the opposite, remember, B and H are weird. So let's do that. 1 times 1/2 is 1/2 minus 3. What's 1/2 minus 3? What's 1/2 minus 6/2, which is 3? It's -5/2. Okay, so my first coordinate transformed went from 1, 0 to -5/2. 2 times 1/2 is 1, minus 3 is -2. 4 times 1/2 is 2, minus 3 is -1, and 8 times 1/2 is 4, minus 3 is 1. There's my transform function. And let's see what we did here. We should expect that it's going to be reflected in the x-axis, but it's going to be shifted up. So if it's reflected in the x-axis, it would have been like this, right? If it was just the reflection in the x-axis. But we're also moving it up by 2. So this was just my, if this was just my A, but then we move it up by 2, so that it would become, that's moving it up by 2, but then we shrink it horizontally and move it to the left. So it's gonna, I mean, it's gonna look something like this at the end. I'm not a graphing calculator, and I refuse to be a graphing calculator. Okay? But that, it's gonna look something like this. Now, go to Desmos, desmos.com, if you want to do some graphing, and I'm gonna include this. Desmos.com, if you want to see what the transform looks like. Desmos.com, something you probably need to learn how to do anyways. Okay, that is transforming logarithmic functions. We always multiply our vertical and horizontal transformations first, and then we do the h and the k's. Okay, that's all I'm going to do for this video. I think that's enough to get you guys going. So thank you very much. Happy quarantine.